Hello, my name is Jin Kim. I'm a research student at Loughborough University. Today I'm going to be presenting hybrid machining in advanced materials. Here is the presentation overview. I'm going to start off with motivation, methodology. I'm going to share some experimental and numerical results. The motivation comes from the difficulties of conventional machining of hard-to-cut materials such as metal matrix composites, known as MMCs. The main reason is due to hard and abrasive particles inside the matrix, for example, silicon carbide reinforced aluminum, as you can see in the microstructure. Machining these type of materials leads to rapid increase of cutting forces, mainly due to high tool wear rate, resulting in bad surface topology, and therefore in many cases require cutting fluids which are not environmentally sustainable. Hence, improved machining processes are required to address these challenges, such as hybrid machining process. Hybrid machining combines one or more additional machining processes into one system. There are many candidates for hybrid machining, but we focus on two assisted processes using ultrasonic and laser to benefit from the known challenges. Schematic images shows the usage of ultrasonic and laser in turning processes. The hybrid machining process has potentials to not only assist the cutting process, but also in some cases to provide conditioned surfaces after the cut. So, advantages of hybrid machinings are listed in the blue box here. The main advantage of UAM is reduction in average cutting forces caused mainly by the tool-chip separation. The separation leads to less tool-chip interaction that is beneficial to the tool, such as less formation of BUE. The surface quality can also be improved by polishing effect of the vibration, and so on. For LAM, the main advantage is the localized thermal softening before the cut, where the softened area can be removed straight after by the tool. In general, if the heat is well absorbed, the radial forces are reduced, resulting less flank wear. Therefore, hybrid machining, combining the two, can be advantageous, but in this presentation the main focus would be on ultrasonic assisted turning. For turning, major vibration is applied either in cutting or feed direction. For cutting is to lower the tool chip friction, and feed is to maximize the polishing effect. When the major vibration is applied in the cutting direction, critical cutting speed exists for tool chip separation to be present. The equation for ideal case is described in the formula, where F is the frequency and A the amplitude. Vibrational mode can be 1D, 2D or 3D elliptical depending on your transducer design. In most cases, perfect 1D motion of vibration is difficult due to mass sensitivity of the total design. To achieve the best surface quality for 3D elliptical with major vibration in the cutting direction, large tool radius and low feed is required for a polishing effect to be maximized. The piezoelectric transducer is self-designed and manufactured for major vibration to be longitudinal along transducer axis. The design process includes λ/4 length from the nodal plane to provide maximum vibration at the transducer tip, where the tool is located. The simple case of lambda can be obtained by speed of sound of mass material over desired operating frequency. The whole design was validated by performing modal and harmonic analysis in the simulation. The result comparison between the simulation and prototype is shown in the table. The frequency for the manufactured prototype was shifted to obtain stable reciprocating motion of vibration. Hence, amplitude is lower than the model. The video shows the major vibration motion, but there are some inevitable radial and feed vibration due to the design of the mount. Therefore, the vibration mode was 3D elliptical. Critical cutting speed is obtained by the formula, but in reality, critical cutting speed is expected to be a lot less due to dampening of vibration by the cutting force. The experimental setup is shown in the image. The transducer was bolted on the force measuring dynamometer, and the setup was adjusted to locate the transducer tip at the top center of the workpiece. It was empowered by power amplification devices, and frequencies were controlled by the waveform generator. The forces were measured in real time using the oscilloscope and plotted in the software. The experimental parameters and workpiece specification are shown in the tables. The method was to compare results of conventional turning, represented as CT, with ultrasonic assisted turning using low-cost carbide tools. Third experiment was performed to compare the conventional turning result using high-cost PCD tools. Two different types of silicon carbide reinforced aluminum alloy, having different volume fraction and particle sizes, were used also for comparison. A real-time cutting force results are shown in the plot. As it shows in the blue curve, average tangential force for CT was 42.8 newtons for 217xg, whereas for UAT, the average force was 18.7 newtons, showing approximately 56% reduction in the average tangential force. The radial force for the same material was also reduced by approximately 42%. For 225xc, UAT reduced the average tangential and radial forces by 32 and 28% respectively. For both workpieces, the force reduction was due to toolchip separation and intermittent radial vibration. Feed force was only reduced for 217xg due to dampened vibration caused by hard silicon carbide particles for 225xc. The forces were much more stable for both CTs using PCD tools compared to carbide tools, but tangential forces were higher due to more impact acting on hard PCD tools, whereas soft carbide tools allows the particles to be embedded on the tool surface. The radial force for 225xc was higher than tangential force using carbide tools for both CT and UAT. Slight chattering was happening on both CTs for 225xc, which caused higher fluctuation of the forces. The machine surface profiles were taken using non-contact surface analyzer. The raw images are shown on the left, and depth profile using the cutoff length of 800 micrometers are shown on the right. For UAT, track marks in the raw image shows the radial vibration is present. The distance between each mark was measured to be 22.63 micrometers, showing slightly dampened vibration compared to free vibration, which was 28.8. Surface roughness values of SA, SP, and SV were all reduced by 33%, 11%, and 32% respectively for 217xg, 53%, 18%, and 5% respectively for 225xc. This was due to reduction of surface damage from BUE and particles. Less chattering on UAT surfaces also resulted in improvement of the surface roughness. Optical microscopic images of the carbide tools are shown. Clearly there is more BUE occurring in CT than UAT. The black area in BUE is predicted as the wear of the tool coating. UAT tend to have more interaction with the workpiece, showing more white area which is assumed to be aluminum. The flank wear cannot be observed through optical microscope, hence requires further investigation. Simulation of the conventional and ultrasonic turning processes were performed. Johnson-Cook plasticity and damage model was used for macroscopic material parameters for the MMC. The equations of the plasticity and damage model are shown in the red boxes. The JC parameters were optimized with the experimental CT cutting force result using PCD tool. Same cutting conditions were applied to the model with the experimental parameters. 3D modeling was performed to accurately analyze the force and hence to obtain the closest JC parameters. The 3D simulation process of CT and UAT are as shown in the video. The maximum ISS stress in the shear band for UAT was higher than CT when engaged, but lower when disengaged, meaning UAT is adding more force onto the chip, but this continuous tool-chip interaction leads to improvement in the average cutting force and reduction of the tool-chip friction. Moreover, the 3D vibration is applying compressive residual stress on a larger area than CT, which in turn enhances the fatigue strength and life. To sum up, hybrid machining UAT is desirable for machining MMCs. UAT is effective only at low speed, low feed with high radius tool, and for materials with high tool-chip friction, materials that requires polishing. UAT is advantageous in terms of average cutting force reduction, better surface finish, less BUE, and inducing compressive residual stress on the surface. UAT is beneficial in terms of lowering tangential and radial forces that reduces lathe shattering. Surface roughness improved with UAT for both MMCs. Simulations can validate the surface quality of the machine surfaces, residual stresses, and the cutting forces. We also would like to mention that we managed to combine ultrasonic with laser, meaning hybrid machining, which showed even better results, and we will report soon. Thank you for listening.